is really the key behind the derivation of the log-log law, so it should be understood. So I have some of that in the notes, but it's actually, I didn't get to complete it. I did some of the WKB analysis, but there's two different regimes in the WKB analysis. There's an elliptic regime and a hyperbolic regime, and then they're connected by a classical turning point, and so you need to use an Array function expansion around the classical turning point, which is done in that's a procedure that's explained in quantum mechanics texts, but it's carried out for the problem at hand in this textbook, which I should have mentioned earlier, by Sulem and Sulem. Textbook. And I think it's called Collapse for Nonlinear Schrodinger Equation or something like that. Nonlinear Schrodinger is in the title. And it was published in 98, 99, around there. So it was right before the rigorous proofs of this log-log law came out. But it includes the construction of the profile and all the details of the heuristic analysis. In fact, Sulem and Sulem were part of this Landman, Papanicolaou, Sulem and Sulem that derived the log-log law heuristically for the first time. So Galina Perelman gave the first proof, the first rigorous proof of the result, and that was by a very detailed spectral analysis of the linearized operator. And then Merle and Raphael, a few years later, over the course of 3 or 4 years, produced a series of papers in which they proved a result which was slightly stronger in the sense that it proves the stability of this blow-up under perturbations in H1, and is also valid for higher dimensions too. So the main contribution in those papers is this local virial identity, so what they call local virial identity, which had first been introduced by Martel and Merle in the context of KDV, and this is the analog for NLS. But it's a type of local smoothing estimate for the linearized equation. And so let me just say a word about it. You start with the virial identity. So we have this V, so V of psi, and that's 1/2 imaginary part of psi bar y dot gradient psi dy. And the virial identity, so even though psi does not solve NLS, it solves this NLS with the 2 extra terms. You have the M and the V, but those have vanishing Poisson brackets with V, and so in fact you still get the virial identity for psi. And so you have that this is equal to 16 times the energy. So then what they do is they plug in psi in the form that we have been working with. So psi is equal to e to the is z plus w, and you get a no, here we are. You get, so when you take psi, expand it as z plus w, then you end up with v of z plus v prime of z paired with w plus I guess 1/2 v double prime of z w w. So that's the Taylor expansion of the functional v with z as the base. Right? All right, so there's the v of z, which you can compute. I mentioned before that when I was doing this, that the z has this asymptotic form. And so that turns out v of z, from that b squared term, you'll pick up essentially b squared here, a constant times b squared. So this v of z is just something times b squared. So I think it's actually minus b over 4. And then we have y q L2 squared. Right, so, oh, I'm sorry, not b squared. It comes from that. It's b. It comes from this vector. Okay. Right. Well, so there's that term. And then this term is subordinate to that because it's one of the orthogonality conditions says it should be. This v prime is minus I lambda z. And so there's j lambda z, and that's one of the orthogonality conditions. And then there's this term, okay, which is the quadratic term in w. And that, so we have ds of that. And what they do is they compute that. Now, what is the evolution, what is ds of v double prime z w w? We have an equation that w solves. It's the linearized equation. And I had written it before. And so when you plug in that equation, then what comes out is a commutator between this operator and the linearized evolution operator. And that commutator is shown to have a positivity property. It's a spectral property. So it's like deriving, if you know in dispersive equations, of deriving local smoothing estimates by positive commutator arguments. But it's at the level of the linearized equation. All right, so this leads to a commutator of a first order operator. You know, v double prime is lambda, so it's a first order operator y dot gradient with a second order operator. So commutator of a first order operator, second order operator, you get a second order operator. So it leads to a commutator which is a positive, which is a second order operator. With a positivity property. And that is, I guess, the best I can do to summarize what they do. So they show that, so you expand out what you have the psi here to second order, and you show that the derivative of the second order term has a contribution of the correct sign. And that assists them in not only deriving the equation that Bs should be proportional to minus sigma, but also in controlling the W. So the details are in their papers, and it's like 4 or 5 papers, in each of which is at least 50 pages. So it's all there for you if you're interested. Okay, so then I'd like to spend the last half an hour putting this into a slightly broader context, in which we have NLS, and we've been talking so much about the critical case. So a lot is known about the critical case. Okay, so we have the NLS, there's a P, and the P was the critical P. And so that's the smallest P for which you can have blow up. Once P is less than 1 plus 4 over D, then the energy and the Gagliardo-Nuremberg estimate will imply that even in the focusing case, its solution is always global. And using this variational aspects of the ground state, it's actually this profile decomposition lemmas by Hamidi and Karani. You can give a proof. Well, actually, the result was first obtained by, I think, Merle and Tsutsumi, Ozawa, perhaps, that any solution, so any solution that blows up must concentrate at least the ground state in mass. So any solution, so here with all this log-log stuff, we were studying solutions whose mass was slightly above that of Q. This is a more general statement. It says any solution U of t that blows up at T star must satisfy concentrates mass at least one point. The more precise statement is that there exists a position x of t, which varies with time, but x of t converges to some x0 as t goes to t star. And we have the limit as t approaches t star of the mass in a window whose radius is shrinking All right, so well, simplify it and just say 1 minus epsilon. Okay, so gradient of u of t goes to infinity as t approaches t star, so we have something here is going to 0. In fact, you have a lower bound on the blow-up rate, so we know that this is going to 0 at least as fast as t star minus t to the 1/2 with the minus epsilon. And so it's focusing in on we're zeroing in on the point x of t, but we're looking at a smaller and smaller neighborhood of it as we approach the blow-up time, and just computing the L2 norm on that shrinking neighborhood. And the result says that in the limit, it's at least q squared. So it concentrates mass at a point, and the mass that's concentrated is at least that of q. All right, so that does not rule out the possibility that you could have concentration at multiple points. And in fact, Merle in the 90s did construct solutions that blow up simultaneously at several different points. But one consequence of this is because mass is conserved, and you only have a finite budget of mass, that you could only blow up at a finite number of points. So hence, can only blow up at a finite number of points. And it's expressed differently. That's the statement that the dimension of the blow-up set is 0. It's a zero-dimensional set would be a finite set of points. So that's in the L2 critical case. All right, so then when we move to the supercritical case, it turns out that you can blow up on a set of positive dimension, in addition to blowing up at a point. So we have this, we started out today discussing this ansatz by Zakharov, where you blow up at the origin according to the self-similar law, following the Z profile. That happens. So you can blow up at a point, but you can also blow up on sets of positive dimension, as I'll describe 2 or 3 examples of that haven't been established rigorously. But before I do that, let me just follow up on this. So we have this property. So then the question is, so we call x0 a blow-up point if this happens. And the question is do we have equality? So in the examples that we dealt with here, with this log-log law or with the blow-up solution obtained via the pseudo-conformal transform, you concentrated exactly Q in mass at the blow-up point. This is just the lower bound. So the question is the mass going in the blow-up, is it quantized? Does it have to be exactly Q? And probably not. It could probably be the mass of excited state solutions to the ground state equation. So look at the ground state equation, Q minus Laplacian Q minus Q, and it's 4 over D in this critical case. Q equals 0. So if you go to the early paper that constructs these solutions by Beresticky and Lyons, this is from the early 80s, then you'll see it's a 2-part paper. In the second part, they construct in dimension 2 and higher excited state solutions. So if we put a sub k here, then for k equals 1, 2, and up, there are solutions, all of which are radial, and then the masses are increasing as we go up in k. So the ground state, so you have Q, we have k equals 1 is the ground state. But then k equals 2 is the first excited state. This is x equals 0. It's the first excited state. And so forth. You have higher order excited state solutions. And it's so the ground state is constructed by calculus of variations minimization problem. The excited state solutions are constructed by the mountain pass method in variational analysis. Right. So we have Q's that solve the same equation, but they increase in mass. And it's conceivable that the excited state profiles could be blow-up profiles just like Q is an approximate blow-up profile. In fact, there are some papers that I referenced in the notes, because I actually think that this is it's a relatively unexplored area that should be better understood, is that just like you can pass from Q, the ground state, to Z, you can pass from QK to a ZK. And this was investigated numerically and heuristically by Budd, Chen, and Russell in 99, so not like within the last decade, roughly. And then some rigorous results were obtained by Rothschild and Caper. So there's some evidence that excited state profiles could be blow-up profiles.
The
Yes? Oh, you're right. It's actually, it does have a 0. You're right. You're right. So I should, it does have a 0. It's not positive. That's right. It's real, but it's not real and radial, but it's not positive. Right. Yeah. So as further evidence that they could be blow-up profiles, there's some papers by Fibbich and collaborators doing numerical simulations showing in the L2 critical case the existence of solutions that blow up on a ring and where the radius of the ring contracts. And he matches the blow-up to some excited state profiles, but not exactly. So it's like he has to cut it off. But it looks like that's the correct starting point, is to think of excited states as being some kind of first-order approximation. And then he looks at numerically at the blow-up rate for those solutions and does not find a log-log correction. So he just sees the self-similar rate, the t star minus t to the minus a half. But he does have to cut off the profiles. The profiles, not the q's, but the z's that would be derived from the q's have infinite mass, so they do have to be cut off. So it's possible that, although he's not seeing a log-log correction, it's possible that it's because it's something like log, 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 or something numerically just completely invisible. So it's still an open problem whether it's possible to have blow-up. So in the L2 critical case, is if question. And I don't recommend working on this because I think it's probably too hard if you're just getting initiated to the subject. But if U of t blows up at t equals t star, is the limit as t approaches t star, the gradient of u of t times t star minus t to the 1/2 equal to infinity. That is this necessarily going to infinity slightly faster, at least slightly faster than that? Or is it possible that, as Fibbich seems to see in his numerics, that this is equal to a constant times the reciprocal of that? So-called self-similar, right? I think Bourgain has this book on NLS, and I think conjectures that in the book. Okay, so that was a little bit of a tangent. Yeah, so what I was saying is that we have mass concentration at blow-up points, and there's only a finite amount of mass to go around, and so we can only blow up on a set of dimension 0 in the critical case. So now what happens in the supercritical case? Well, what we can do is, so in the case P bigger than 1 plus 4 over D, blow up on a set of positive Hausdorff measure. So just say positive measure. Yeah, all right, Hausdorff. A set of positive Hausdorff dimension. Is possible. This has been demonstrated in a few examples. this actually comes down to effectively a dimensional reduction by a symmetry assumption. So we start, so if you take the case of p equals 5 and any d greater than or equal to 2. So when d is equal to 1, p is equal to 5, that's L2 critical. But when d is equal to 2, p is equal to 5, that's H1 half critical. So it's a supercritical case. Then you can blow up on a sphere and blow up on a sphere, which we might as well take to be at radius approximately 1. Any radius. And the idea behind this was introduced by Raphael in 2005. And he did the 2D case. Is you take Q to be the 1D P equals 5 ground state. Which incidentally is the hyperbolic secant to the power of half up to a constant. It's explicit in 1D. All right, and then in the 2D problem, then in 2D, past the polar coordinates, or actually you can do this in any dimension. So in DD, in D dimensions, make a radial assumption. So take U of R to be radial. It's a radial function, and prescribe a solution to leading order, which is like the L2 critical blow-up, but at radius 1. So this would be 1/2 and Q, which it really, it really should be Z, but actually, so it's essential to pass, I should say, it's essential to pass from Q to Z in order to derive the log-log law, because the B, it was essential that we understood what the B was doing. But then the B is going to 0, and so you can, after the fact, go back from Z to Q if you just want to describe the blow-up. So. All right, so we have lambda, so all these are depending upon P, of course. Where now R of T is converging to some point which is around 1 as T goes to T star. Okay. All right, so why does this work? It says Q is this 1D ground state. And so U being a d-dimensional function with the radial assumption solving NLS, we should write NLS in polar coordinates as I dtu plus d minus 1 over r dru plus dr squared u plus u to the 4u equals 0. And if all the actions, so this is concentrating becoming singular at radius 1, so if the singularity is around radius 1, then R here is approximately 1, and the dru is subordinate to the d squared ru. This gets worse when you take more derivatives in R, because the lambda pops out. The lambda is going to 0. So this term will be much smaller than this term. And so to a leading order approximation, you get rid of it, and you have 1D quintic NLS. And that's why taking Q to satisfy the 1D ground state is consistent. So all this has to be justified, of course. When you actually perform the analysis, you take a solution of this form, you add a w. Actually, usually you add a w here, but you add the next order term. And then you have to plug it into the full equation. You can't ignore that term, but the contribution of this term from the leading order q piece is shown to be subordinate in the analysis. And so the picture of what we're doing here in the 2D case would be in the plane. We have 0, we have the circle at radius 1, and then the lambda is going to 0, so we're talking about a solution which sort of lives in a little ring where the ring radius is, so the ring radius is lambda of t, and it's shrinking. So it's contracting towards the circle, and then it's very steep in the circle. It's very, very tall, but concentrated. So you find that in order to construct this in dimension 2 and 3 and higher, what you have to understand back at the L2 critical level, the regularity of the solution away from the blow-up core. So you need better bounds on the solution away from the blow-up point than are furnished directly from the Merle and Raphael L2 critical machinery. And so in the case of d equals 2, Raphael used a local smoothing estimate to prove d equals 2. Raphael used local smoothing. To show h1/2 boundedness away from the blow-up point. And then in this application, the 2D case, 2D is h1/2 critical, and so that suffices. What you have is on the ring itself, it's the L2 critical analysis, and you use the Merle and Raphael machinery. But inside the disk, you have a genuinely 2D situation, and so you have to bound the solution in h1/2. Bounding in L2 will not suffice, which is something as you work with nonlinear dispersive equations, you come to appreciate the nature, the importance of the critical norm, controlling the solution in the critical norm. In 3D quintic is h1 critical, and so you actually, this argument does not suffice, and so to handle the d equals 3 case, I did this with Svetlana Rudenko. And what we had to do was show that L2 critical solutions away from the blow-up point are actually bounded in H1. And to do that, we had to take the equation and project to high frequencies, that is, the frequencies above the blow-up rate, and prove a boundedness for high frequencies by using bilinear Strickert's estimates. And then for lower frequencies have a sort of a finite speed of propagation attached to them. And so you have lower frequencies can't move away from the cannot move out of the blow-up core too fast. And so those were automatically controlled by finite speed of propagation. All right, so a different machinery was necessary to do it in 3 dimensions. So we get an open set in the radial function space of solutions that blow up in this fashion. But okay, about dimension. It's in 2D, you're getting blow up on a circle, 1-dimensional. In 3D, you're getting blow up on a sphere. It's two-dimensional. So you're getting code dimension 1 blow up in the case p equals 5. So now another version of this initial result that I did with Svetlana was to work in 3D cubic. So if you take d equals 3, p equals 3, and assume that u has the form of, is cylindrically symmetric. So you assume that u of x is u of rz, where, so this is cylindrical coordinates. And then you sort of install a 2D cubic, which is again L2 critical, blow-up solution at, so you put a 2D cubic blow-up at RZ 1, 0. And a similar kind of analysis goes through. And so the corresponding 3D picture is one in which you have an annulus, a concentration in an annular neighborhood of the circle in the xy plane.
So when you talk about positive outdoors measure,
Yes.
you mean d minus 1. Because in the first example, you have to count the outdoors measure equals the number of the points. And the set is 0.
Yeah, the positive, so the Hausdorff dimension is 0 in that case, right? So in the L2 critical case, the Hausdorff dimension of the blow-up set would be 0, right? So what did I write in the case P? Yeah, and now positive Hausdorff dimension is possible, right? So here we see where the dimension is 1. So dimension is 1 for the d equals 2, p equals 5. That's been shown to be possible. And dimension is 2 for d equals 3 and p equals 5. That's possible. And here I've shown that for d equals 3, p equals 3, dimension 1 is possible because I use cylindrical coordinates and I get blow up on a circle, but the contraction is in an annular neighborhood around the circle. Okay, so these are all games that you can play by using symmetry assumptions for higher dimensional equation to effectively reduce the dimension, and then you install an L2 critical blow up at a point in the reduced dimension. But then when you view it in the original framework, it's a higher dimensional object. So what you could conjecture out of all that is that you can where did I write it down? Yes, so that you can put, so 1 plus, so P, how did I say it here? Sorry, so P equals 1 plus 4 over the reduced dimension, which would be d minus h. So if h is equal to the dimension of blow-up set, then when passing to the critical problem, it should be d minus h. And so we're getting a situation where h equals d minus 4 over p minus 1. Dimension of the blow-up set is, so like for example, when d is equal to 3 and p equals 3, we're getting a one-dimensional example in the cylindrical coordinate set. So then the conjecture would be that this is an upper bound for the dimension of the blow-up set. Because you can still blow up at a point in the supercritical case. So the dimension set could still be 0. Dimension of the blow-up set could still be 0, but maybe these are sort of the largest sets on which you can blow up. So that's that's an open problem that I have no idea how to prove such a general statement. Now there's other things you can do, like for this d equals 3, p equals 3 case, you can blow up on a sphere if you allow, which is two-dimensional, which would seem to violate this conjecture, but you have to allow the sphere to contract as you evolve into the blow-up. And that's just done by choosing a proper ansatz, but I don't have enough time to explain that. But that was a recent work that we did last year with Rudenko and Galina Perelman. So because I wanted to end with at least one or two open problems, let me just can name a few of them quickly. So these are not totally out of reach, in the sense you have to get proficient in the subject before considering them, but it'd be the kind of problem that I would be comfortable suggesting to a graduate student. One is blow up. So in all those cases where we constructed blow up on a set of higher dimension, it was circle or sphere. How about blow up on an ellipse in, so say in 2D quintic? So I isolate that problem because in 2 dimensions you can use complex analysis to give you conformal mappings, right? So you can conformally map an ellipse to a circle, and then the result of that transformation will be that the coefficients of the Laplacian, if you look at the equation, the coefficients of the Laplacian will be distorted, but in a computable way. And in that form, it's not too hard to suggest at least an ansatz for a potential blow-up candidate. So I discussed that in the notes. Secondly, there are a few other equations that have similar features to NLS for which this log-log blow-up should be taking place, but it has not yet been proven. One of them being so-called elliptic Davies-Stewartson. Which is discussed in the Sulem and Sulem book. In fact, the Sulem, Papanicolaou, and Wong have a paper in which they numerically investigate this situation. And so it's a coupled system, which there's an NLS-type part and then in this case, an elliptic equation that is sort of a generalization of NLS. So the generalization of 2D cubic NLS. So they have this numerical paper in which the blow-up looks to be very similar, except that the profile is a little anisotropic. If you don't like systems, though, you could look at this 4-NLS or biharmonic NLS. And so here the numerical papers that you should look at are by Fibbage. So there's a choice of P that makes this L2 critical. And in that case, the blow-up has been studied numerically at least. And you could try to just carry the whole procedure over for this modified equation where now the Laplacian is replaced by Laplacian squared. So it's mentioned for the references that there's papers by Fibbage that discuss it numerically. And then you can also look at Fibbage's papers on a vortex blow-up. Where instead of the Q ground state, you look for a ground state where the Q is radial, Now you look at e to the im theta q of r. So you look for a q tilde m of r theta, where you've now included a angular face, and then require that this solve the ground state equation, and that will give you an equation for qm that is, has the extra m term coming from the angle. And then they show numerically that you can blow up with this kind of profile. And that has recently been proven by Gideon Simpson and Ian's wires when m is equal to 1, but it's an open problem for m greater than equal to 2. All right, and then there's these excited states that I think is a nice source of open problems. But I listed a couple in the notes if you're interested. So thank you for attending this. It's a pleasure to come here.
Thank you.
Okay.